Welcome to our lecture on panel data basics. So I'm going to talk today about the simplest possible panel data model, and the notation will look pretty similar to some of what we saw in our last lecture on clustered standard errors because, in fact, panel data is an example of clustered sampling. So we're going to imagine today that we observe xit and yit repeatedly over time for the same individuals. So I have a very simple linear model here. Yit equals alpha plus beta xit plus uit. The index I denotes people, and I runs from 1 to capital N. And t, that index denotes time. That runs from 1 to capital T. So we're observing multiple people in multiple time periods. Now, the reason why this is a case of clustered sampling is because, indeed, we would expect there to be dependence within observations for the same person over time. So if we sample you, that means we observe you for all time periods, and probably your observation tomorrow is going to be very closely related to your observation for today in ways that actually can matter for standard error calculations. Now, in last lecture, we talked about some abstract grouping variable, g. So if you want to translate from the notation from last time, which was generic, to the notation for this time, which is more specific to the panel data case, then in last lecture's notation, what was G will become I today, and what was I will become T. So we're going to be assuming IID observations between people. In other words, we're going to be thinking about randomly sampling the I dimension from some population. So this is like randomly sampling the clusters. All right, so let's introduce the simple one-way error components model. So I'm going to take that error term uit from the previous slide, and I'm going to decompose it into two pieces. The first piece is eta I, and the second piece is epsilon it. Epsilon it is what I'll call the idiosyncratic error. This varies over I and t. And epsilon it could be correlated with epsilon is. So in different time periods, these things could actually be correlated with each other for the same I. For today, I am just going to assume that the covariance between epsilon it and xit is 0. So for today, I'm going to be assuming that these idiosyncratic errors are not a source of endogeneity. So we're actually going to be thinking today about a model in which beta can have a causal interpretation. The individual effect eta I, on the other hand, varies across individuals but is fixed over time. So when the covariance between eta I and xit is equal to 0, that is traditionally called random effects. When the covariance between eta I and xit is not 0, it's traditionally called fixed effects, and I just want to let you know that I completely hate this terminology because it's deeply misleading. But because it's so standard in economics, I'm going to refer to it anyhow. So while there's nothing about this eta that means it must be viewed as a fixed quantity in one context and a random one in another, there's nothing at all, in fact. We could view it as random regardless of whether it's correlated with x. Again, the traditional terminology calls the setting where eta and x are correlated fixed effects, and the setting where they're not, random effects. So what is the role of this eta I? Well, it creates within cluster dependence. You may remember the example that I showed you in our cluster standard errors segment from the robust standard errors lecture. It was a very simple example where all the groups were exactly the same size, and there was, in fact, a common group-specific error term. Well, you may remember from that example that there was a correlation parameter that we defined in terms of the idiosyncratic and the group-specific errors, and that's exactly what this eta does. So if we suppose that epsilon it is IID across both I and t, well, then if it's uncorrelated with eta I, then we're going to get that this sigma eta squared over sigma eta squared plus sigma epsilon squared will be the correlation between uit and uis. So my point here is that this eta I will create within cluster dependence even if the epsilons themselves are not dependent over time. Now, the epsilons may be, it may be that within a given individual, these kind of time-specific errors, these epsilons, could be dependent. But even if they're not, the mere presence of that eta I, this is the error term that is constant across time but varies across individuals. The mere presence of that error is going to create correlation between you in one period and you in another period for the same person. And again, there was a more fully worked out example of that in the previous lecture. Now, we could also view this eta I as a kind of unobserved confounder. So in particular, if the eta I is correlated with xit, well, then that's going to make xit endogenous. So perhaps eta I is some kind of time invariant omitted variable. It has to be time invariant again because it has only an I subscript and no T subscript. So in a wage regression, maybe you could think of eta I as some kind of ability. And if you want to think about it that way, it would need to be a sort of ability that does not improve as you spend more years on the job or as you get more education. All right, now today's lecture is relatively brief, and there are fairly long exercises for you to carry out on your own. The reason for this is that we're getting to the end of the course, and by now you know quite a lot. So it's time for you to transition from passively absorbing knowledge to actively creating knowledge and actively unconfusing yourself by trying out experiments and playing around with data sets. So here's, again, a fairly long exercise. I'd like you to download a data set that I created. It's called Fake Panel Data because it's simulated. You can download this from my website. And I simulated it from the one-way error components model described above. Here is a description of the columns. Now, something I want to point out to you here is that because this is simulated data, I'm actually providing you with the epsilons and the etas. In a real data set, you would not have access to the errors. You'd only have access to x and y. But I'm providing them to you so that you can see a little bit more about how I generated this data set. So here I've got a list of different exercises I'd like you to carry out. This is a very interesting, I hope you'll find, panel data example that I've created, which will give some very strange results, or I should say very different results, depending on how you run your regressions. So as usual, I'd like you to pause the video, spend some time to work through this example, and you can check your solutions against mine from the course website. Fixed effects regression. Well, I hate the term, but here's what it is. This is equivalent to adding a dummy variable, which is to say a binary variable, for each individual in the panel, and then removing the intercept. So this is the same thing as saying that there is a person I specific intercept. You can do this again by having a dummy variable for every single individual and getting rid of that intercept. So this will soak up, or sort of absorb, remove, any endogeneity from the covariance between eta and xi not being 0. And mathematically, it's equivalent to running OLS after you subtract the individual time averages. So what do I mean there? Well, we start with this model yit equals alpha plus beta xit plus eta I plus epsilon it. Then if we define y bar I to be the average value of y for person I, averaged over all time periods, and proceed similarly for xi bar and epsilon I bar, then we can write a regression model, yit minus yi bar, and we will see that that model eliminates eta I. It also eliminates the intercept. So if you were to run this regression without an intercept, you would get the coefficient, you would be estimating this coefficient beta, and you would have removed the presence of eta I. There are, however, some gotchas. So the first gotcha is explicitly adding dummies for each group will make your computer explode if there's a large number of groups. I strongly advise against doing that. Second of all, doing this demeaning operation by hand and then running OLS will not actually give you the right standard errors. And the reason is that you actually lose a degree of freedom for each of these n time averages that you're estimating. So they really are estimated parameters, and the standard errors need to take account of this. So there's another gotcha that you've got to be aware of. Once you run a fixed effects regression, you're no longer going to be able to include any time invariant regressors in your model. They would be perfectly collinear with these individual specific dummy variables. And another way of looking at this is they would also disappear, just like eta I, when you subtract the group means. Now on the problem set, you're going to see a very interesting example of how to fit a model that is very closely related to fixed effects, but actually does allow you to include time invariant regressors. So I won't say anything more now. I want to avoid spoiling the surprise. But if you are running fixed effects, you can't include time invariant regressors. So don't do it by hand. Use a package. And there are several packages in R that can provide fixed effects for you. One is lmrobust, which we saw in our last lecture. This has an option called fixed_effects, so if you'd like, you can use that one. There's also a package called PLM, which is a very powerful package for panel models in R. And if you use the PLM command from this package and set model equals quote within, that will give you fixed effects. PLM has a tremendous number of features, but personally I find it quite hard to use. There is actually a whole book written about it. There's a lot of documentation online. So depending on what you want to do, you might want to take a look at the PLM package. But my preference is actually for the function FEOLS from the package fixest. And as usual, I've got some links on the slides. Here you can see PLM package and fixest package. So you can read more about how these packages work. Fixest is my preference. It's fast, it's flexible, and it's very easy. Let me show you just how easy it is. As we've seen for IV, R supports what are called two-part formulas, where you use a vertical bar to separate the model from some other aspect of the formula. And FEOLS uses this same kind of syntax. So our first argument is formula, and our next argument is data. An example of a formula would be y tilde x plus w, vertical bar, person ID plus year. What does that do? Well, it runs a regression of y on x and w with fixed effects for person, so person ID, and year. So that would actually be a two-way fixed effects model. By default, it will not display the fixed effect estimates, because in general, if you have a lot of them, you don't want to see them. They would just fill up the whole screen. By default, it will also cluster the standard errors on the variables after this vertical bar, although you can override that. There are millions and millions of alternative standard errors that you could use here. I'm exaggerating only slightly. If you want to read more about that, you can click on this link. And one note that you may want to bear in mind is that it can sometimes be hard to exactly match the fixed effect standard errors that were computed by someone else. And the reason is there's so many different finite sample adjustments that are in wide use that people are not always so scrupulous about documenting exactly what they've done. This can be frustrating. Sometimes we can get close, but we can't exactly match what others have done. That's a pity, but there are many options available in this package. It's also really fast. I believe that it is in fact the fastest package for estimating fixed effects that is currently available. That may have changed, but at the time when I wrote these slides, that was definitely the case. Here's a quick example of FEOLS, which plays very nicely with tidy from our favorite package Broom. So I'm going to pull in my fake panel data, and I'm going to run a fixed effects regression of y on x with, I'm going to include only person effects. So this is the one-way error components model, and then I will tidy the result. And there you go. You can see that in my simulation, the relationship between x and y was actually -1. And wow, look how statistically significant that is. It's almost as though I simulated it. If you wanted to include the year effects as well, you could do that. You would just need to add person plus year. In this particular case, it barely changes the results, and the reason is that there were no year effects in my simulation. And now it's time for another exercise. This one's a bit shorter. I would like you to take a look at the simulated data set from above. And basically, what I would like you to do is I would like you to carry out some fixed effects estimates, or rather carry out some fixed effects estimation by hand. So I'm asking you to demean these individual observations using dplyr, then run OLS with these classical standard errors and see what you get. So I would just like to drive home the fact that it actually does not give the right result. Now, a couple other exercises for you to do here as well. So please, as usual, pause the video and give these a try. Once you're all done, you can check against the solutions. Well, we've talked about fixed effects, so now we've got to talk about so-called random effects. With the random effects model, we claim that eta I and epsilon it, um, actually that is a typo, so that is a typo there. It should say if eta I and xit are uncorrelated. So I wrote epsilon by mistake. Apologies, I will fix that. So if eta I and xit are uncorrelated, then there's no endogeneity for the fixed effects to soak up. But they will still soak up some of the variation in the regression, and the result will be an estimator with kind of a needlessly higher variance. So this is an inefficient way to proceed. You might say, well, the nice thing about fixed effects is I don't care if x is correlated with this eta I or not. I will always be identifying the effect that I want to. And the point is, that's true as far as it goes, but actually you'll have an estimator with a higher variance if, in fact, there is no covariance between eta I and x. You didn't need to do that, and you're going to be shooting yourself in the foot. Now, you could just ignore these eta I's. You could just run plain vanilla OLS. But in fact, that wouldn't be quite right either, because these eta I are going to create within cluster correlation. So in spite of the fact that there may be no endogeneity induced by eta I, again, assuming for the moment that eta I was uncorrelated with x, and pointing out that I have a typo on the slide, apologies for that, you would still need to take account of this cluster dependence if you wanted to get the right standard errors. So this is where random effects enters. If you actually believe that x is uncorrelated with eta, then there is a very simple approach using GLS that corrects the standard errors and yields the efficient estimator at the same time. So you're killing two birds with one stone using generalized least squares. This does rely on assumptions, and the usual approach, although it's not the only approach that you could take, but the usual approach is to assume that the idiosyncratic errors are uncorrelated across time for the same individuals. This GLS idea, I mentioned in our previous lecture on clustering that you could take an active or a passive approach to things like heteroscedasticity or even cluster dependence. You either try to model it and fix the dependence, or you don't model it and fix the standard errors. Well, here we're in the situation of trying to model it and correct the regression. So what we're going to do here is we're going to need to rely upon some assumptions. That's the price of using an approach like this, using an active approach. So if that assumption holds, then we can run an OLS regression of yit minus theta y bar on xit minus theta x bar. And it turns out that that will give us exactly what we want. So we can just run this regression, and we can just report the usual standard errors from that regression. The trick, of course, is we don't know what theta is. So what is theta? Well, theta is 1 minus this complicated-looking formula. It's the square root of the variance of the idiosyncratic error divided by the sum of the variance of the idiosyncratic error plus t times the variance of this time invariant error. Now, the key thing about this theta is that it's between 0 and 1. So compared to fixed effects is like setting this theta equal to 1, because fixed effects demeans each observation relative to its time average, so yit minus yi bar. Well, here, when we run random effects, we don't subtract y bar, we subtract theta times y bar, where theta is actually something that we estimate from the data. So we're going to need to figure out what theta is by getting some estimates of sigma epsilon squared and sigma eta squared. So if theta is equal to 0, then that's just the same thing as pooled OLS, where you run OLS tossing all the observations in and completely ignoring the fact that some of those observations are the same people over different time periods and some are different people. Again, as I said a moment ago, when theta is 1, this is just fixed effects. But of course, we've got to estimate theta. How do we do that? Well, one way we could estimate it is by using the residuals from OLS and fixed effects, although I'm not going to get into that in too much detail. Just to sort of show you what's involved, you would need to compute some kind of estimate of sigma epsilon squared and sigma eta squared. So let's do it using PLM, which will take care of all the details for us. So first we need to load the package. If you haven't installed it, you'll need to do that first. Second of all, we'll be using my fake panel data set from above, but we will need to make sure that the variable year is stored as a factor. So you probably remember from an earlier lecture that a factor is R's name for a categorical variable. So in this particular data set, I can't recall if I had stored year as numeric or if I had stored it as character, but I did not store it as factor. So I'm going to convert it now to factor data because that's what the PLM package wants to see. Now I will run in line 6 my random effects regression, which I will store in an object called random effects. I'm going to use the PLM command from the PLM package. I specify my formula, y tilde x. I specify my data set. And then I specify my index. So the index is going to show me which is the unit identifier, so which is the I index, and that's person, and which is the T index, that's year. Now I'm setting model equals random. That's going to give me random effects. And just for fun, I'm also going to run fixed effects using FEOLS, and I'm going to run plain old OLS just using LM. Now I will put everything together for you in a nice little table using our favorite package model summary. And let's have a look here. All right, well, the results are different. So OLS gives a different result. By far, in this case, as you probably saw when you played around with this simulation, I set it up to make sure that OLS would give a really misleading answer. And indeed it does. So let's ignore OLS because it's just spectacularly bad, but also notice the OLS standard error is actually quite big in this case. It happens to come from the way that I set this model up. Okay, but OLS has lots of problems. Let's ignore it. If we do random effects, what are we going to get? Well, we're going to get approximately the right answer, so that the correct value of that slope was actually -1. So we have, in fact, an estimate that's quite close to that. Oh, I'm sorry, I misspoke. I'm reading. I was just reading from the random effects column. Let me read across to the fixed effects column first. Sorry. So the fixed effects column has no intercept because it shouldn't, because it's equivalent to demeaning every observation relative to its time average. So the average over time periods for a given person, and we're getting very close to the correct answer of -1. We have a standard error of 0.05. And here we have the random effects in the estimator in this case, which actually is extremely similar. So -0.986. And the random effects estimator can have an intercept. That was the point that I wanted to make a moment ago. There's no reason that it can't. It's not demeaning anything. So the random effects estimator could have an intercept. It could have as many time invariant regressors as you want. That would work. But of course, they're supposed to be different, right? So why are they getting such similar results in this particular case? Well, let's try to take a peek here. So I mentioned before I didn't want to get too far into the details of how you run random effects. All right, but now that we've seen some simple results, let's look under the hood a bit and try to understand what's going on here. So I'm going to produce a little estimate. Actually, I'm going to be using the errors themselves here. So I'm not going to be estimating anything, but if you remember in the fake panel data set, I actually gave you the variables eta and epsilon, so I don't need to estimate them. So in some sense, I'm cheating here, but I want to show you why, given the way I simulated the data in this example, the random effects and the fixed effects estimates were so close to each other. So what I'm going to do first is I'm going to go and figure out approximately what the variance of eta was. So technically in line 1, I am estimating that, but I'm estimating it from the actually known errors that I gave you from the simulation study. So in my data set, I told you what those etas were. So what we're doing here is we're going to take out the very first eta from each person. And the reason that eta is actually repeated for every time period, it's time invariant, so it's in there for every single one. So we only need to get the first one. And I'm going to use the first one from every person to construct a data set of all those etas and compute the variance for those guys. That's S eta squared. Now I'm going to do the same thing for epsilon, but for epsilon, I'm going to use all the observations of epsilon because they vary across time for the same individual as well as across individuals. So there's no need to just pull out the first one, the epsilon from the first time period, because epsilon varies across time. And then finally, I'm just going to figure out how many time periods there are in this panel, and t Okay, let's take a peek. So there's 5 time periods. Sigma epsilon squared is quite small. It's about 0.01, whereas sigma eta squared is quite large. It's about 3.7. So now we can use the formula for theta to figure out why random effects and fixed effects were so similar in this particular example. And the answer is, well, yeah, actually, this theta is very big, right? So you can take a look at the formula for theta, and you can see a couple of facts. First of all, so the question is, when is theta going to be close to 1? Well, theta is going to be close to 1 when this square root thing is close to 0, right? And when theta is 1, that gives us fixed effects. So when will this square root thing be close to 0? Well, it's going to be close to 0 when the denominator is much bigger than the numerator. Okay, so when is that going to happen? Well, let's take a peek. Let's look at the numerator and denominator. They both have sigma epsilon squared in them, so that's going to be effectively a wash. Now let's look at nt times sigma eta squared. So what this says is when there is more variation in sigma eta squared, relatively speaking, when that is quite large relative to sigma epsilon squared, then that denominator is going to be larger. So the fraction is going to be smaller. So the square root is going to be even smaller, and then we're going to get a theta that's close to 1. We can also ramp up the number of time periods. So if the number of time periods gets really, 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 really big, then similarly, the denominator gets really big, the fraction gets really small, and the square root makes it smaller still, so we're quite close to 1. So that's what's going on in this example. The particular simulation design that I used happens to make it be the case that the random effects and fixed effects estimators will be similar, but in real life, they won't necessarily be. All right, and we will end with a little exercise for you to play around with, where I would like you to download a wage panel dataset from the Wooldridge package, run a few regressions, try random effects, try fixed effects, and try to see if the results vary. In my little simulation, they didn't, but in this one, maybe they will. This example is based on a paper from Vella and Verbeek in 1998 that you can take a look at if you want. And you can also take a look at how your results of the effect of union membership vary across these 3 different specifications.